So in the last video we have seen what actually impedance is. Now we will see how the network elements behave in AC circuits. We will take individual elements and we will see what their behavior is in AC circuits. Now the very first one, it will be the resistor. So as shown in the figure, this is a simple circuit where I'll be giving a single phase AC supply. As already mentioned in the last week, this is the representation of the sinusoidal signal. So this is the peak value and this is the sine term, and omega represents the angular frequency, which is generally given by 2 pi f, where f is the frequency. So this type of AC signal is provided to your resistance. Now it allows a current to pass through it. So at any point of time, so this is the mathematical expression of this signal. Okay. So for 1 whole cycle, what is the time taken? That is called as t, and omega is equal to 2 pi by t. So when you know these two terms and the angle at which it is being delayed, it is now 0. So I can write this one as Vm sine omega t plus phi, where phi is the phase angle difference between the reference point and the start of the wave. Now in this case, phi is 0. So normally for inputs we take it as 0 unless otherwise mentioned. So this is the mathematical expression. So the voltage at any instance, at any point t, can be obtained using this equation by just substituting the value of t. Let us suppose if I want to calculate it here, let us suppose this is 0.5. So I can write Vm sine omega 0.5 and I can get the value. Okay. So this is the way how we represent. Now this is an AC signal which is being applied to your resistor. Now what happens when it is applied to your resistor? Okay. So before going for that, we'll take the current as I, as already said in the previous week. Now this is your sinusoidal signal which is your applying. So this is your resistor, right? So this is V of t, which is represented by Vm sine omega t, and this is your R, right? So whatever the current which is flowing in the circuit, you know, I is equal to the voltage at any point by the impedance offered by this element. So the impedance offered by this element, or in this case, I'll take it as directly, I is equal to V by R. So when I take this one, what I'll get? Vm, V is already Vm sine omega t by R. Okay. So if I consider this particular term as Im, so I'll get Im sine omega t. See, this is also a sinusoidal signal with no phase angle difference. Okay. So which means that when you allow a AC signal to pass through a resistor, the phase angle initially, whatever the phase angle which you do have for the voltage signal, it remains the same for the current signal also. Which means that if your voltage signal is like this, then the current signal also will start at the same point and at the same point and end at the same point. But there will be a difference in the magnitude. So it might be like this. There is no phase difference. Both are starting at the same points. Okay. But the magnitudes, they will be different. This is Vm, this is Im. And what is the relation between Vm and Im? It is Im is equal to Vm by R. This is what I have written here. Okay. Try to remember this one. When you are allowing an AC signal, see, this is the representation. So this is your Im. Only there is a difference between the magnitudes. Okay. So there is no phase angle. So if I represent V like this, then I also will be on the same line. This is called as a phasor diagram. Is there any angle between V and I? No, there is no angle between V and I. There is no phase difference between V and I. Okay. Now, We'll move on to the inductor circuit now. How inductor behaves. This is the inductor. The same voltage signal I am applying here to the inductor, and I'll be calculating the currents. In an inductor, we have seen what is the equation? V is equal to L di by dt, right? So if I write it in a reverse way, so what I'll be getting? See, this is the equation, right? Where V is the voltage and I is the current which is flowing, and L is the inductance. So, V can be replaced by Vm sin omega t. Right, so I am writing it as Vm sin omega t is equal to L di by dt. Now you bring this one to this side. So what I'll get? Di by dt is equal to 1 by L Vm sin omega t. So if I want I, what I should do? I should do integration of this entire term. Right. This differentiation, if it goes to this side, it will become integration. Integral dt. Now if you carefully see in these terms, only this term is variable with respect to t. These two are all basically constants. So what I'll do is, see, I'm just removing those from the integral term because those are constants. So this is my expression. I is equal to Vm by L. These are constants. Integral sin omega t dt. So when you integrate this one, what is the integration of sine? It is minus cos. And since you do have omega, you will get it in the denominator. Okay. So this is your expression for currents. Now, your V signal is Vm sin omega t. Whereas your current signal is minus Vm by omega L cos omega t. So it's not easy to compare. So what I'll write it as Vm by omega L, it is minus cos omega t. So I'll write it as cos can be written as sin 90 minus theta, right? So I'll write it as sin 90 minus omega t. And I'll push this one because minus sin theta is sin minus theta, right? And also cos theta is sin 90 minus theta. So I am just replacing these two trigonometrical equations. So if I push this one, minus will go inside. So it will become omega t minus 90. 90 means pi by 2, right? Because 2 pi is 360. So pi by 2 is 90. So I am replacing this 90 with pi by 2. So this is what I have written here. So I is equal to omega Vm by omega L sin omega t minus pi by 2. And this I'll take it as Im. So I can write this one as I is equal to Im sin omega t minus pi by 2. This is my expression, where Im is nothing but Vm by omega L. Now, if you carefully see, this is my voltage term, this is my current term. The magnitudes may be different, but see the phase angles. Here the phase angle is 0. Here you do have a minus 90 degrees phase angle. Okay, so which means that, see, if this is the voltage, see this black one is the voltage, current will be starting 90 degrees after the voltage. It will be like this. So it is because we have got Vm is equal to Vm sin omega t, I is equal to Im sin omega t minus 90 degrees. So current will be lagging the voltage by 90 degrees regarding the angle. Regarding the magnitude, magnitudes are also different. See, this is Vm, this is Im. And the relation between these two is, it was omega L, right? And this particular term, or I can rewrite this one, Vm is equal to omega L into Im, right? This particular term is called as impedance. Okay, the ratio of voltage and current is generally called as impedance, right? So this is impedance. Okay, and I'll call this one as reactance. Since it is displacing by 90 degrees, so I'll give it as J omega L. Okay. So if I write it as a complex number, so what is this component? This component was X, right? So that's why omega L is treated as X. Okay, this is the inductance. So I'll take it as inductive reactance. Okay, and also see the phase angles. The phase angles are differing by, this is only phasor representation, not a magnitude representation. Phasor representation. See, the voltage and the currents, they are separated by 90 degrees. And E is leading. So I'll take in this way, in the anti-clockwise direction. So E is leading when compared to I. By how much degrees? 90 degrees. Okay. Similarly, we will go now, inductive reactance. As already said, omega L is treated as XL. You know omega value is 2 pi L. Try to remember this formula. Inductive reactance. Okay, and what is the relation between Im and Vm? Im by omega L. And what is omega L? XL. Okay, now we'll move on to capacitance now. How a capacitor behaves in an AC circuits. So again, I am taking a same sinusoidal signal and I am applying it to a capacitance. You know, a capacitance basically stores energy in the form of electric fields, and that's why it is called as a condenser. Now, see, this is the voltage which I am applying. Okay, so what is the equation for relation between V and I? Right, you know, I is equal to dq by dt, whereas q is written as CV, right? This is capacitance, this is voltage. If I assume C is constant, so I can write it as, see, charge of the capacitor at any point is C is equal to Q by V. This is capacitance. It is given by C is equal to Q by V. And the current flowing through the circuit is given by I is equal to dq by dt. If I replace Q with CV, I'll get I is equal to dCV by dt. I'll assume that C is constant, okay? Because in my AC circuit, C mostly will be constant. So assuming C is constant with respect to time, your equation was this one, right? If C is constant, it will come out. So I is equal to C dV by dt. And what is V? V is Vm sin omega. If I replace this one, Vm is again constant, I can bring it out. So d by dt of sin omega t is cos omega t, with additionally omega will be there. Okay, so these entire terms are constant terms. So omega c Vm. Okay, and see, sine, here it is cos omega t. See, what is cos theta? I can write it as sine 90 plus theta is also cos theta. Okay, so that's why I am mentioning it as sine omega t plus pi, right? Now if you carefully see, V was Vm sin omega t. I is equal to omega c Vm sin omega t plus pi by 2. Okay, I'll take this one as Im. Okay, so I'll take it as Im. See the magnitudes. The magnitudes are different. Okay, but see the phase angles. This is 0, this is plus pi by 2, which means that it is starting ahead of voltage. So, yeah, this is the expression. I think I have written in the previous slide itself. So, capacitive react. I'll show you the figure, right? So, this is the voltage. See the current, the red line is starting somewhere before this voltage signal, 90 degrees ahead of this voltage signal. Okay, and how the phasor diagram will be? If I take voltage here, current will be leading. Current will be leading by 90 degrees. Okay, and this is the phasor representation. Okay, now how to determine the capacitive reactance? As already said, capacitive reactance, see what we get, Im is equal to, I have taken omega c into Vm, right? So what is the ratio of voltage and current? 1 by omega c, right? This is termed as impedance. But since it is a change, right, it is creating a phase angle. So I'll take it as 1 by j omega c. Okay. Z is equal to 1 by j omega c. What is 1 by j? It is minus j, right? What was the actual expression of z? It was r plus jx. You compare this one with this one. What you will be getting? Right? x is equal to 1 by omega c. I am considering only the imaginary parts. Okay, because there is no real part, considering only the imaginary part, x is equal to 1 by omega c. And since this is due to capacitance, I am taking it as x is equal to 1 by omega c. Okay, so hope you have understood the response of network elements in AC circuits. A quick look about the properties. Okay, see the property. Resistor, it opposes the currents. Inductor, it opposes change in current. Capacitor, it opposes change in potential drop opposite. And resistor is represented by R, inductor through L, capacitor is represented by C. And the units. Resistor is measured in ohms, inductance is measured in henries, capacitance is measured in farads. And the VI equation, here V is proportional to I, V is proportional to di by dt, and hence it is written as V is equal to L di by dt. And here it is I is proportional to dV by dt, I is given as C dV by dt. These are the time domain equations. Try to remember them. Time domain equations. You will come across till your final year. And energy and power. Here active power is consumed and energy is dissipated in the form of heat. These both consume reactive power, that I will tell you in the next slides, don't worry. But here energy is stored in the form of magnetic field by the inductor, whereas in case of capacitor it is stored in the form of electric fields. And what is the impedance of it? It directly offers resistance. They offer reactance which is equal to omega L. This offers capacitive reactance which is equal to 1 by omega c. Okay. And the impedance of it. This is R, this is j omega L, and this is minus j by omega c. Okay. So with this, I'll stop this video, and in the next video, we'll discuss problems on simple AC circuits. Okay. Thank you.